Fuel flow begins as the fuel pump pulls fuel from the fuel tank to the fuel filter. Fuel flows through the two combination fuel filter water separators. These filters are 98% efficient 10-micron filters. After water and contaminants are removed, the filtered fuel flows to the gear pump section of the fuel pump. The QSK-23 engine utilizes a fuel pump which pulls the fuel from the tank and generates the system fuel flow and pressure. The pump output pressure is controlled by the ECM through a pressure regulating actuator. The ECM receives a signal from the fuel pressure sensor indicating the fuel pressure from the pump. The ECM then adjusts the PWM signal it sends to the fuel pump actuator to increase or decrease fuel pressure. This is accomplished by adjusting the actuator flow area to control the amount of fuel bypassed to the inlet side of the fuel pump. The fuel pump supplies fuel to the Electronic Fuel Control Valve Assembly, or ECVA. Fuel flow through the assembly is controlled by a shut-off solenoid valve and two fuel actuator valves. The ECVA uses these devices to control the fuel flow into the timing and metering passages. The fuel metering flow is controlled by the fuel shutoff valve and the fuel metering actuator. Fuel from the inlet first flows to the rapid restart fuel shutoff valve. When the valve is energized, it opens and allows fuel to flow to the fuel metering actuator. The actuator is an electronically controlled spool-type control valve. The coil receives a PWM signal from the ECM. Depending on the duty cycle of the PWM signal from the ECM, the spool uncovers a portion of the inlet port and allows fuel flow. The fuel metering rail pressure sensor monitors this pressure and sends this information to the ECM. The timing rail actuator receives fuel flow from the fuel inlet. The ECM sends a signal received by this actuator to control fuel flow to the timing rail. The timing rail pressure sensor monitors the pressure in the timing rail and sends this information to the ECM. The fuel from the ECVA flows through piping to the intake manifold. The fuel for the rail and timing is fed to the front and rear sections of the manifold by the external plumbing. To maintain equal pressure at each injector, the passages in the intake manifold each feed 3 cylinders. The fuel flows from the intake manifold to passages in the cylinder heads. Passages in the cylinder heads deliver timing and metering fuel to the injectors. Timing and cooling fuel from the injectors returns to the fuel drain in the fuel manifold. Drain fuel travels from the cylinder heads to the intake manifold drain passage. The line connected to the fuel drain fitting directs the fuel to the OEM-supplied fuel cooler. The OEM is responsible to ensure that the maximum fuel inlet temperature at the fuel pump does not exceed 71 degrees centigrade. From the fuel cooler, the fuel flows back to the fuel tank.
The following section will cover fuel pump operation.
At cranking, where we need maximum fuel going to the engine, the fuel pump actuator is closed. The supply pressure and the controlled pressure are both equal. Hence, the bypass valve is closed and all the fuel goes to the engine. While cranking the engine, the pressure should be approximately 241 kilopascals. As the pressure increases, the bypass valve, the actuator, and the relief valve work together. The ECM reads the pressure from the sensor. The actuator opens, causing the controlled pressure to decrease. This causes the bypass valve plunger to open, allowing the fuel to pass through that valve and back to the pump inlet. The relief pressure valve is always open above 241 kilopascals. Some fuel is always bypassed through this valve when the engine is running. The maximum pressure valve is normally closed. When the pressure goes above 2,896 kilopascals, for example during motoring or maximum speed, then the engine does not need fuel, and that valve opens to let the fuel recirculate back to the inlet.
The following section will cover injector operation.
The QSK-23 injector assembly contains 3 individual moving sections: the lower plunger, the timing plunger, and the upper plunger. All of the plungers are coated with titanium nitride to resist scuffing wear and provide maximum service life. The lower part of the injector is very similar to the PT injector. One important difference is that the lower barrel and nozzle are one piece. This design eliminates a high-pressure joint. The lower section consists of a lower plunger return spring, nozzle, nozzle retainer, spring retainer, and a non-adjustable spring housing. The open nozzle design of the injector provides the ideal rate and shape of injection. A slow start of injection allows a slower burn at the beginning of combustion for reduced combustion noise. The sharp end of injection eliminates secondary injection and provides reduced hydrocarbon emissions. Additionally, the QSK injector incorporates an angle drilling in the lower plunger that enhances plunger seating. This drilling allows fuel, which is trapped in the seat, to escape and spill back into the drain passage. This process is referred to as trapped volume spill, or TVS. The QSK-23 fuel system provides infinitely variable injection timing. The timing is varied by controlling fuel pressure to the injector timing chamber. The timing section consists of a balance orifice, timing plunger, bias spring, and deflector ring. The timing plunger is positioned in the barrel bore below the upper plunger. The upper section of the injector consists of the barrel, spring housing, return spring, upper plunger, and plunger link. Now let's take a look at an injection cycle. We'll start the injection cycle with the cam follower on the outer base circle. All 3 plungers are in contact with each other. As the camshaft rotates, the follower rolls toward the inner base circle. All 3 of the plungers begin to retract. When the lower plunger retracts far enough, the rail feed port is uncovered and fuel is pressure time metered through an orifice into the cup. Remember from PT theory, the P is rail pressure and T is the time that the feed port is uncovered. The rail pressure is controlled electronically and can be as high as 1,379 kilopascals or as low as 14 kilopascals. The time depends on engine speed. As the plungers continue traveling up, the lower plunger is in its fully retracted position when the spring retainer contacts the ledge on the barrel. The cam follower continues to roll toward the inner base circle, allowing the timing and upper plungers to continue moving upward under spring force from the return spring and bias spring. When the upper plunger retracts far enough, it uncovers the timing feed port and fuel is PT metered through an orifice into the timing chamber. As the cam follower starts up the injection ramp of the camshaft, the upper plunger moves down and closes the timing feed port to end timing metering. The fuel that was metered into the timing chamber is now trapped between the upper plunger and the timing plunger. The amount or volume of fuel metered into the timing chamber determines the separation between the upper and timing plungers. The amount of separation determines the effective combined length of the upper and timing plungers. This length determines when injection starts. Changing the overall combined plunger length changes the start of injection. The separation between the plungers varies from 2 millimeters at minimum timing advance to around 9 millimeters at maximum timing advance. This separation is sometimes referred to as over-travel. The trapped fuel becomes a solid hydraulic link between the upper plunger and timing plunger. When the timing plunger contacts the lower plunger, all three plungers move down together. As the lower plunger moves down, the rail feed port is also closed. This ends the metering of fuel in the cup. The quantity of fuel trapped in the cup is the amount of fuel that will be injected. The timing and upper plungers have a diameter of 15 millimeters compared to the 12 millimeter diameter of the lower plunger. This difference in diameter reduces the pressures in the timing chamber to approximately 60% of the injection pressures. Because of this difference in pressure, the pressure in the cup can be as high as 172,000 kilopascals, with only 104,000 kilopascals in the timing chamber. This reduction ratio allows the injector train to operate with minimum stress and wear, yet still produce extremely high injection pressures. The downward velocity of the plungers increases as the follower continues up the injection ramp of the camshaft. When the pressure in the cup exceeds the pressure in the cylinder, injection begins. Injection ends as the lower plunger makes contact with the nozzle seat. For every injection cycle, the stroke of the lower plunger is 10.5 millimeters. At approximately the same time, the groove in the timing plunger aligns with the groove in the barrel, opening the spill port. The timing fuel then spills as the upper plunger continues its downward movement. During this spill process, the flow area between the timing plunger and the spill port regulates the fuel pressure in the timing chamber to keep a load on the lower plunger. This pressure is necessary to prevent the lower plunger from lifting before mechanical contact occurs between the upper and timing plungers. A spill ring is positioned over the spill port to act as a pressure deflector to prevent damage to the injector bore in the cylinder head from continual release of high-pressure fuel. As all of the timing fuel spills from the chamber, the plungers make mechanical contact. The downward travel of the injector train continues, creating a mechanical crush condition on the lower plunger. This ensures that the plunger remains seated in the nozzle during combustion. Now that we have seen each step of the injection cycle, let's take a look at the complete cycle again.